All right.
Okay, so good morning. We're gonna start electric field analysis this morning, continuing with static electricity. Now, the concept of an electric field might be a little bit different, or might be a little new uh, to you. But continuing an electric force, we established that there's a force between charged objects, and we we did we gave the formula for the force. The force between, say, two charged objects, whether it's attractive or repulsive, that force is equal to K, which is a constant, times the charge on one of the object times the charge on the other object divided by the square of the distance, the separation distance between those two charge objects. That's the force. Now, the electric field, if you can just imagine, you have a charged object, and all around this charged object, there is a force, because it's actually a force. So it's a force, it's an invisible force that is around this charged object. So what we're saying is that that charged object is going to change the space around it. Okay, this is what we call the action at a distance force. It's, remember again, electric force, just like magnetic force, is a non-contact force. There's no contact between anything, but it's exerting a force. So again, remember, opposite attract. Okay, there's no contact between these charged objects. Opposite attract and repel. There's a repulsion between like forces. And so just imagine that there is a charged object, and all around this charged object, all the space around this charged object, there is an alteration in that space. So there is a force. So if say for instance you have this charged object, and if you bring a similar charge in that space, it's going to repel it. If you bring a sorry yeah if you bring a similar a light charge in that space, it's going to repel it. If you bring an opposite charge in that little space, it's going to pull it towards it. Okay, so that is what we call the electric field. Okay, the electric field is the space around the charge that is altered, and that electric field, it has a strength. There's a force towards it, and it can be either attractive or repulsive. So any object in that space is going to experience this electric field strength. Okay, the strength of the field depends on the amount of charge that the object has and how far away uh, the other charged object is from the originally charged object. So if you have a charged object, all around that charged object, all around it, there's going to be a force associated with it. And that's what we call the electric field strength. Again, if you bring up a light charge in the field, it's going to pull it towards it. If you bring a light charge, it's going to repel it. Light charge is going to repel it, but if you bring an opposite charge, it's going to pull it towards it. Okay, the force with which it's going to pull object towards it is called the electric field strength. And just like when we have your Van de Graaff generator, and say if it's charged positive, it's gonna have an electric field around it, and that electric field is gonna have a certain amount of strength. Okay, it's gonna have a certain amount of force. That electric field around the charged object is gonna have a strength. And the electric field strength, okay, is dependent on, okay, before we move on to electric field strength, you have to understand the concept of source charge. So the if we talk about an electric field strength, it is the electric field strength of a charge object. And that charge object that we trying to find the electric field strength is what we call the source charge. So you have an object and it has a charge. We call that the source charge. Now, if you bring another charge in that space, we call that second object test charge. So you have an original object and you want to, you have an originally charged object. That's what we call the source charge. And then you bring a second charge object in that field. We call that a test charge. The electric field strength of the source charge, okay? So the original charge object that you have, the electric field strength. So again, it's like it's like a force. The electric field strength, that is the space around this charge object that's either going to attract or repel, is defined as the force divided by the charge. So it's the force exerted by the source charge divided by the charge, okay? And it's the charge of the test charge. So the source charge is the originally charged object that you have, and then you bring a test charge in that field you're testing the strength of the electric field. The electric field strength is equal to the force between these two charge objects divided by the charge that is on the test charge. Now, remember, so this is the definition. Electric field strength is equal to E, and it's defined as the force exerted between these two charge objects divided by the charge on the test charge. So one is the source charge, the other is the test charge. So remember, force is going to be in Newton, charge is going to be in coulombs. So the unit of that electric field strength is newtons per coulomb. Remember that force is equal to K, or Coulomb law constant, times the charge on this. This is the source charge, big Q. This is the test charge that you brought in the field to test the strength of the source charge. And then you're going to divide by the square of the distance, separation distance between the two charge. So if you're going to divide the force by the charge on little q, the little q going to cancel out. So you'll find that the electric field strength is equal to K. Q, that's the charge on the source charge, divided by the distance squared from the test charge. If you look closely on the formula for electric field strength, it has nothing to do with the test charge. Electric field strength, when you simplify it, is equal to K, which is the Coulomb law constant, times the charge, the amount of charge on the source charge, divided by the square of the distance between the source charge and the test charge. So the strength, the amount of charge that the test charge has no bearing on the formula. So the electric field strength of a charge object. So any charge object is going to have a certain amount of electric field strength. And that electric field strength, that is the space around this charge object, is going to attract or repulse, depending on the amount of charge that the source charge has, divided by the square of the distance. So you bring in a test charge with a lot of charge, it's not going to influence the electric field strength of this original charge object that you have, which makes sense because the electric field strength of this object is related to the amount of charge that the object has. Okay? And again, electric field strength is in the unit is Newton Coulomb. So again, Now we're talking about how do we draw electric field lines. Okay, so we draw lines to represent electric field strength. Or electric fields, we draw lines to represent them. And the lines have direction. The convention is to think of the test charge as positive. And if you can get this concept, you don't have to memorize anything. So just imagine you have a source charge. You have a charge object, and it's going to have an electric field around it. It's going to be attractive or repulsive. You don't know. But the convention is to think of the test charge as positive. If the test charge is positive and the source charge is positive, they're going to repel each other. So the electric field strength is going to be away from the source charge. You always keep the test charge positive. The test charge is positive and the source charge is negative, there's going to be an attraction between them. So what's going to happen now? The electric field strength is going to be towards the source charge. So a positive source charge is going to have electric field lines going away from it. And a negative source charge is going to have electric field lines coming towards it. Think in terms of just your test charge. Your test charge is always going to be positive. Okay? This is the charge that you brought in the field of the source charge. Test charge is always positive. So if your source charge is negative, it's going to pull it towards it. So the lines are going to go towards the source charge. If your source charge is positive, because the test charge is always positive, it's going to be repulsive. The lines are going to go away. Okay? So positive source charge would create an electric field that would be repulsive. That means the lines are going to go away from it. And a negative source charge would create electric field lines that are attractive. Okay? So we have a few questions. We're going to quickly answer them and then move on. So charge Q acts as a point charge, so the source charge. It creates an electric field. So there's an electric field around it. Its strength is measured in, its strength measured at a distance of 30 centimeter away is that. So this is electric field strength, force per charge, 40. What is the magnitude of the electric field strength that you would expect to be measured at a distance of 60 centimeters away? This basically points towards the definition of electric field strength. So again, the concept here is electric field strength E is equal to K, that's the Coulomb law constant, times the charge on your source charge. That is the source charge, divided by separation distance squared. So, charge Q acts as a point charge and it creates an electric field. So you have an object with a charge, it creates an electric field, and its strength measured. So you're measuring the strength at a distance of 30 centimeters away. The electric field strength is this. What is the magnitude of electric field strength you would expect at a distance? So the electric field strength varies with the distance squared, the square of the distance. So if the distance is 60 centimeters away, you don't have to plug 60 centimeters in the equation. You know that at a distance of 30, the field strength is this number. So at a distance which is twice 30, so if you increase the distance by 2, you have to square it. So your electric field strength is gonna decrease by 4, by a power of 4. What is electric field strength is inversely proportional to the square of the distance. So if the distance increase, the electric field strength is going to decrease. If the distance decrease, the electric field strength is going to increase. And the electric field strength varies directly with the amount of charge that is on your source charge. Electric field strength is going to vary inversely with the square of the distance. What that means, the further away, the less the electric field strength. The closer towards this source charge, the greater the electric field strength. And the greater the charge on the charge object, the greater the electric field strength. So if your distance is doubled, so distance doubled, when you square it, it's going to be 4. So you have to decrease the electric field strength by 4. So you have to divide this by 4. So the new electric field strength will be 10. If you get closer now, if the distance is a half, so 15 is a half of that, so you have to square the half. So when you square the half, it is 1 over 4. So your electric field strength is going to increase by a power of 4. So it will be 4 times 40, that's 160. And now if it's 90 centimeters away, then this is 90 is 3 times this distance. So you square 3, that's 9. So you're going to decrease the field strength by 9. It's just basically, it's a simple way to look at it. I mean, you could plug these numbers in the equation, but you're gonna go through a tedious task of working out the mathematics. But if you just realize that your electric field strength varies with the square of the distance, inversely with the square of the distance, and directly with the amount of charge, then the concept would be crystallized. All right, so let's move on. All right, so charge Q acts as a point charge to create an electric field. So you have an object which is charge Q. Its strength measured at 30 centimeters again away. So you put a test charge in the field to test it. You're testing the source charge, and the strength is 40 newtons per coulomb at 30 centimeters away. What would be the field strength if 30 centimeters away if you double the charge? Again, if you double the charge, because electric field strength varies directly with the charge. So if you double the charge, it's going to double the electric field strength. Because if you multiply this by 2 to get 2 times Q, you have to multiply this to maintain the equation. So the electric field strength is going to be doubled. So you're just plugging it in the equation. That's all you're doing. And then, so, that concept is, and then this question, the following unit is certainly not, this is not our standard unit. Because we know that the unit of electric field strength is force divided by charge, which is Newton divided by coulombs. So the following unit is certainly not the standard unit for expressing the quantity of electric field strength. We know that. But they give you this. Is this, however, could this be accepted as electric field strength? If you remember the definition, electric field strength is equal to the force. This is kilograms times meter divided by second square. I remember what Newton's law said that. Newton's law said that force is equal to mass times acceleration. So this is a force. It's just not our regular unit. As a matter of fact, this is the Newton. Mass times acceleration is the force, and it's Newton. So this is the force, and then divided by coulombs is the coulomb. So this is actually another way to write electric field strength. Force divided by charge. Force, as Newton second law states, force is equal to mass, kilogram, acceleration, meters per second square. Okay, so this is another way to write it. So this is correct. That formula is correct. All right, so let's move on. All right, so let's just look at this question. So a negative source charge is shown in the diagram. So this charge is negative. This source charge can create an electric field. So any charge object will create an electric field. It's going to alter the space around it, either attractive or repulsive. Various locations within the field are labeled, all these. For each location, draw an electric field vector in the appropriate direction with the appropriate relative magnitude. That is, draw the length of the vector, long whenever the magnitude is large, and short whenever the magnitude is short. So basically, the concept here is this is negative. Okay, so all these, the distance, look at the distance. The closer the distance, the greater the field strength. Okay, the closer the distance, the greater the field strength. If this charge is negative, if this is negative, the direction of the electric field line, remember now, if you have a positive test charge, you always have a positive test charge. If this is negative, it's going to attract the positive test charge. So the lines are going to go towards the lines are going to go towards the negative source charge. Okay, because if you have a positive test charge, the negative source charge is going to attract it. So the lines are going to go towards. Okay, the closer the distance, the greater the electric field strength. So that is the concept right there. All right, let's all right. So continuing with our electric field lines, the greater the charge, the greater the density of the line. So the lines, the electric field lines will give you a lot of information. Remember what we said. To determine the direction of the electric field lines, you have to think in terms of a positive test charge. So if you have a negative source charge, it's going to attract the positive test charge. So the lines are going to go towards that negative source charge. If you have a positive source charge, remember your test charge is positive, so it's going to be repulsive. So the lines are going to go away. When you repel, you move something away. However, another important point is that the greater the charge, so remember when we talk about greater charge, we're talking about the source charge. The greater the charge, the greater the line density, more of the lines you have for a certain amount of space. The lines are always perpendicular to the surface. So these are convention for drawing electric field lines. Okay, the greater the line density, that's the more lines you have, the greater the amount of charge. The lines are always going to be perpendicular to the surface of the source charge. Lines cannot be at an angle. They always have to be perpendicular. Lines usually do not cross each other. Okay, they're going to be parallel. They're not going to cross each other. And the lines represent the direction and the strength of the electric field within a region of space. And this is what we mean, okay? All right, so this is simple. Don't think in terms of being negative. So uh, so these are, you have a source charge here and you have another source charge. So if you have two negative source charge, so remember, just look at the first one. The lines are going to go towards the negative charge, because if remember, in order for you to draw the lines, the direction of the lines, think in terms of a positive test charge. So if you have a positive test charge and your source charge is negative, it's going to pull the test charge towards it. That's why the lines move towards the charge. So lines going towards, so if you have a negative charge object, the lines are always going to go towards it. The lines have to be perpendicular, 90 degrees to the surface. The lines not going to cross each other. They're going to be parallel. They're not going to cross each other. The greater the charge, the greater the line density. Just look close to the source charge, this one. Close to the source charge, you can see the lines sort of bunch up. Remember distance? Distance is in the denominator and you square in the distance. So the closer the distance, the greater the charge, or the electric field strength. And then when you move away, see it space out a little bit more, because the larger the distance, the electric field strength is going to be less. Electric field strength is equal to K times Q divided by D squared. K, the Coulomb law constant, Q is the amount of charge that's on this, and D is the distance. So the greater the distance, the less the electric field strength. So it's spaced out. So it's less density the further away you get, the lines space out, showing you that there's less electric field strength. Closer towards the charge, okay, the electric field strength is greater. You can see it crowd. So if you have two negative source charge, you can draw the lines, because the lines have to go towards the charge. Because if you think of a positive test charge, it's going to attract it, and that's how you're going to get the direction of the lines. Okay, and then when you can see that the line, when they are all around this charge object, you're going to have an electric field, but the lines cannot cross each other. When you're drawing the lines, they cannot cross each other, and that is why they sort of separate right here. They cannot cross each other. This is two negative charge. If you have two positive charge now, sorry, a positive and a negative charge, remember what we said about a positive charge? To determine the direction of the lines, you have to think in terms of a positive test charge. Always think in terms of a positive test charge is always positive. So if you have a positive test charge, this source charge is going to repel it because they have the same charge. So the electric field lines are going to be away, because it's going to repel this positive test charge. Remember what we said, negative source charge. If you have a positive test charge, it's going to attract it, so the lines are always going to go towards it. So you draw it for this. So these two are going to attract each other. So the lines will come this way and they'll go this way because it's moving away from the positive and it's going towards the negative. Moving away from the positive, going towards. This is how you draw a positive and a negative charge. You can see that you don't have this stuff going there because this is a repulsion. This is telling you that these are similarly charged negative, so they repel right here. The lines cannot cross each other. The line density, so you can see closer to the charge, the lines crowd. You have more density because you have more electric field strength. As you move away, you can see the lines space out. Greater distance, less electric field strength. So They could give you this in an exam and, ask you questions about it. All right. All right. So this is for two positive now. So again, remember when you have a positive source charge, positive test charge, it's going to repel it, so the lines are going to move away from the charge. It's going to move away. Closer to the charge, you can see the lines bunch up. There's more density. It's so because the distance is smaller. So the electric field strength is greater. So you represent that by the line density. The line density will give you an idea of the electric field strength. Okay, so positive and positive. So the lines are going to move away from the charge. Okay, but they're not going to cross each other there. They're going to repel. Okay, they're going to repel each other. All right, so let's do some questions now to see if we understand what's going on. So the first question is, several electric field line patterns are shown in the diagram below. Which of these patterns are incorrect, and explain what is wrong with all the incorrect diagrams. So let's look at diagram A. So this is a positive charge. We know that a positive charge, the lines are going to go away. We know that. And the reason, because if we have a positive test charge, we always have a positive test charge. This positive charge is going to repel it, so the lines have to go away. So this is correct. Let's look at B. Negative test charge. If you have a negative source charge, test charge is always positive. So it's going to attract your test charge. So the lines are going towards it. So this is correct. This is correct. All right. So this is a positive. We know that positive, it's going to repel the lines. Remember, the arrowhead tell you the direction that the lines are traveling. This should be away. This should be away. Okay. Okay. And then let's look at this one. This is positive. The lines are away, but the electric field strength, the electric field strength is uniform around a charged object. You see, it's bunched up, right? The line density is greater here and it's less there. No, the electric field strength is the same around a charged object. Remember, electric field just means that the space around the charged object is going to be altered. It's going to be attractive or repulsive. All right, so this is incorrect. Let's look at this one. So for a negative source charge, it's going to your test charge is always going to be positive. The line should be going towards it. So this is not correct. The line should be going towards it. All right, let's look at this one. So what is wrong with this diagram? What is wrong with this diagram? All right, so we have two positive charge coming together. Two positive charge coming together. Each of them going to have a field. Each of your charge object is going to have an electric field. So okay, so we know if it's positive, it's going to repel your positive test charge. So the lines should be going away from the positive test charge. Sorry, positive source charge. The lines should be going away. Okay, so this is good. It's going away. And then for this one, they're going away. It should be, but the line should not cross. Remember what we said? The lines do not cross. So this is not correct. The electric field lines do not cross. They are usually perpendicular to the surface of the charge, but they do not cross. All right, let's look at this one. All right, so consider electric field line shown in the diagram. From the diagram, it is apparent that object A is, so which is negative and positive? You can get this. This is like a question that you'll get. All right, so let's look at A. The electric field lines are going towards A. So we know that A has to be negative. Remember, A has to be negative because If you have a positive test charge, it's going to attract, this is attracting it. And it can only attract a positive test charge if it's its opposite charge. So it has to be negative. So A is going to be negative. Okay? And so it's gonna the electric field lines are gonna go towards A. So you draw them towards. And then what about B? The electric field lines are going away from B. So if you have a positive test charge and this is positive, it's going to be repulsive, so it's going to go away. So this is negative, that's positive, and this is something that you'll get in the exam. But you have to know that. You have to know that the lines going towards a charge is negative, going away from a charge is positive. Okay? All right, let's look at this one. Consider electric field lines drawn at the right for a configuration of two charges. So you have two charges coming together. Each of them going to have electric field strength around it. Several locations are labeled on the diagram. Rank these locations in order of electric field strength from smallest. Again, if you're talking about, you have to look at the density. The more dense, the more charge. The closer it is, the greater the strength. Okay? So if the lines, the greater the density of the line, the greater the electric field strength, and then the further away you are, the less the electric field strength. Remember the formula. Electric field strength, when we simplify it, is equal to K times Q divided by D squared. All right, let's look at this one. Use your understanding of electric field lines to identify the charges on the objects in the following configuration. All right, so let's look at this. A, the lines are going away from it. So if the lines are going away from it, it has to be positive. Because if you have a positive, remember your test charge is positive. So if the lines are going away from it, that means it's repelling the test charge, which is positive. So it has to have the same charge. So it has to be positive. Lines going towards this, that means it's attracting the positive test charge, going to be negative. Let's look at these two. All right, so you have one there, one there. So this is going away and this is going towards. So C is positive, D is negative. Okay. Okay, so C is positive and D is negative. Let's look at these. You have E and F. Going towards is negative, away is positive. And then you have 3. You have 3. Okay, but the concept is still the same. Going away is positive. Going away is positive. Going away is positive. So they're all positive. Again, the lines should not cross. The lines should be perpendicular to the surface. The density of the line, that means if they're crowding, the density of the line will tell you that will give you an indication of the electric field strength. It's greater when the density is the line density is increased, and if the line density is decreased, then it's less. Okay, so that's the concept of electric field lines, electric field strength. Remember, lines going towards a charged object is negative. Lines going away from a charged object is positive, such as the source charge is positive. Okay, the lines do not cross. Lines do not cross.